introduction. For this project, we are analyzing a real-world dataset using mathematical modeling. Our main goal is to determine the best fit curve, whether it's linear, quadratic, or cubic, using the least squares method. The dataset we choose is called Annual Dates by State, which was published by the Department of Statistics Malaysia, or DOSM. This dataset records the number of deaths registered each year based on the usual state of residence of the disease. We selected this dataset because it shows clear annual variation, which make it suitable for observing patterns or trends in mortality over time. So, in this project, we apply the linear, quadratic, and cubic models to identify which mathematical equation best represent the trend in the data. Next, we will look at the data provided by DOSM, which shows the relationship between the number of deaths and the crude death rate. As we can see here, this is our data. So, this slide shows the data that we use for our project. Here, we have the number of deaths, which is represented as S, and the crude death rate represented as Y. Specifically, for the state of Johor, the values are arranged by year, and from the table, we can see that both the number of deaths and the crude death rate increase gradually over time. This gives us a clearer picture of how mortality changes from year to year. This dataset will be the basis for all our modeling later, such as the linear, quadratic, and cubic model. So, understanding the trend in this table is important before we move on to the analysis. The next one is linear model. For the linear model, we use the equation y equals to a plus bx. To express this, we using linear algebra, we rewrite the entire dataset in matrix form. Each data point contributes one linear equation, so we can construct a matrix M where the first column consists of 1. This corresponds to the constant term A. The second column contains the x value, which in our case are the number of deaths. On the right hand side, we have the vector y representing the crude death rate for each observation. Therefore, the whole dataset can be written as a linear system, and v equals to y. And we know that v is equal to a b. We continue to this slide. Because the system mv equals to y generally does not have an exact solution, we apply the least square methods to find the best estimate of the parameter a and b for our data on death and crude death rates. For least square approach gives us the normal equation, which is m transpose m inverse v which is a and b equals to m transpose y. From our computation, we obtain the matrix M transpose M and M transpose Y as shown. Solving the normal equation allows us to estimate the parameters. So we got A is 2.559 and B is equals to 0.0001442. Therefore, the best fit linear model relating the number of deaths to the crude death rate is Y equals to 2.559 plus 0.0001442 as. This model provides the line that minimizes the overall prediction error for our data.
On this slide, we are looking at how to compute the error vector in a linear model. In a linear model, we typically have an observed vector y and a predicted vector mv, where m is the model matrix and v is the parameter vector. The error vector, denoted as e, is imply the difference. So, the formula is e equal to y minus mv. Here, the table on the right shows each component of the error vector. For every data point, we subtract the predicted value mv from the observed value y. The result is the small error value shown in the last column. This error value tells us how far the model's prediction are from the actual data. Ideally, the error values would all be close to 0. This means the model fits well. So, for the magnitude of error, at the bottom of the slide, you can see the magnitude of the error vector, which is 0.588503312.
We extend the model by introducing a quadratic term. In this case, the relationship between the number of deaths, x, and the crude death rate, which is y, is model using y equals to a plus bx plus cx squared. To express the model using linear algebra, we again convert the entire system into matrix form. For each data point, the first column of our matrix M is still consists to 1, representing the constant term A. The second column contains the x value, the number of deaths, and the third column is contain the square value x squared to account for the quadratic component cx squared. On the right hand side, we have the vector y, we store the crude death rate for each corresponding x value. With this structure, we can write the quadratic model compactly as mv equals to y, where v is equals to a, b, c is the vector of parameter that we want to estimate. So let's continue. This is the normal equation, seems like linear model before. This least square approach gives us the normal equation, which is m transpose m, v equals to m transpose y. V is known as a, b, c. So from our computation earlier, we obtained the matrices m transpose m inverse and m transpose y as shown. With solving the normal equation allows us to estimate the parameters. We get a is 4.0172, while b is equals to negative 1.60016 times 10 power of negative 5. And lastly, for c, we got 4.18357 times 10 power of negative 9. So we compute all this together and we get the best fit quadratic curve is y equals to 4.0172 minus 1.60016 times 10 power of negative 5 as plus 4.18357 times 10 power of negative 9 x squared.
Now, let's look at the quadratic model. Similar to the linear model, we again compute the error vector, which measure how far the model's prediction are from the actual data. The formula remains the same. It is y minus mv equal to e. The table on the right show the error values for each data point under the quadratic model. Each row compare the actual value y, the predicted value from the quadratic model, mv, and the resulting error, which is in the last column. These errors are generally smaller compared to the linear model. So, for the magnitude of the error vector is 0.4734967.
We extend the model one step further by introducing a cubic term. Here we assume that the relationship between the number of deaths x and the crude death rate y may follow a cubic pattern. The cubic model can written as y equals to a plus bx plus cx squared plus dx cubed. To represent this, using linear algebra, we form a larger matrix M. The structure is similar to the previous models, but now we include a fourth column. The first column contains 1 for the constant term A. The second column contains x, the number of deaths, and the third column contains x squared, and lastly, the fourth column contains x cubed, represent the cubic term dx cubed. The vector on the right y remain the crude death rate for each observation. With this setup, the full system can be written as mv equals to y, where v is equals to a, b, c, d is the parameter vector we want to estimate. The next one is normal equation for cubic model. So the first augmented matrix on the left hand side is the m transpose m we got by the calculate, and for the right hand side is m transpose. As you can see here, this is our least square solution for cubic. A, B, C, D is equal to the first augmented matrix is m transpose m inverse times with m transpose y. We already calculate and put the value on the report and on the slide. So we got the answer. The answer will represent the parameter. The first one is A. A equals to 4.0256. For B, negative 1.0494 times 10 power of negative 5. For C, 4.2583 times 10 power of negative 9. And lastly for D, negative 1.28428 times 10 power of the parameter we already got earlier. We can find the best fit linear curve, which is y equals to 4.0257 minus negative 1.0494 times 10 power of negative 5s plus 4.2583 times 10 power of negative 9x squared minus 1.2848 times 10 power of negative 50x cubed. So that's all for linear, quadratic.
Next, we look at the cubic model, which is a higher degree polynomial model. Just like before, we compute the error vector using the same formula. It is E equal to y minus mv. The table on the right shows the error for each data point under the cubic model. For each value of y, we compare it to the cubic model's predicted value mv, and the difference is shown in the last column. The errors are relatively small, similar to what we saw in the quadratic model. So, at the bottom, you can see the magnitude of the error. It is 0.4735. Then this number represents the overall size of the error for the cubic model. So, even though the cubic model is more complex, it does not provide a noticeably better fit than the quadratic model. This suggests that the quadratic model may already capture the trend well, and adding more complexity does not improve the accuracy.
part, we are going to talk about the graph for scatter plot and best fit curve and error vector against the x-axis for the linear, quadratic, and cubic model. In this part, we are going to talk about the graph for scatter plot and best fit curve and error vector against the x-axis for the linear, quadratic, and cubic model. For the first graph, we plotted the linear best fit curve together with the scatter points of real data. The linear curve is represented by the equation y equals to 2.5593 plus 0.00144x. In this graph, the x-axis shows the number of deaths in Johor and the y-axis is the crude death rate. When we observe the linear curve, we can see that it shows a general increasing trend, which matches the yearly increase in crude death rate. However, because the data has some fluctuations, the straight line cannot follow certain changes in the second graph. We plotted the quadratic best fit curve together with the scattered data points. The equation for this curve is y equals to 4.0172 minus 1.6002 times 10 to the power of negative 5 times x plus 4.1836 times 10 to the power of negative 9 times x to the power of 2. Unlike the linear curve, the quadratic curve has a slight curve shape allowing it to fit the data trend graph. Show the cubic best fit curve plotted together with the scattered data. The cubic equation is y equals to 4.0258 minus 1.7494 times 10 to the power of negative 5 times x plus 4.2583 times 10 to the power of negative 9 times x squared minus 1.2848 times 10 to the power of negative 5 times x cubed. The cubic model allows the curve to bend more than once, making it even more flexible. When we view the graph, the cubic curve also follows the data trend closely, especially where there are graphs for the residual for the linear model. Residuals mean the difference between the actual data and the predicted value. Ideally, residuals should scatter evenly around zero, but here we can see that some points are far from the x-axis. This shows that the linear models make bigger errors at the quadratic model's residuals graph. The points are more balanced and closer to the x-axis. This means the quadratic model has smaller error values. It predicts the value more accurately compared to the linear model. In the cubic residual graph, the residuals are also small and distributed around zero. The curve tries to reduce the error even further. However, the difference in error compared to the quadratic model is very small. This suggests that using a cubic model does not give a big advantage for this data.
So for conclusion, we have a summary of the error magnitude for all three models: the linear model, the quadratic model, and the cubic model. The linear model has the largest error magnitude around 0.5885, while both the quadratic and cubic models have much smaller errors around 0.473. So, based on our result, the best fit models for this dataset is the quadratic model. It provided the most accurate prediction with the least overall error, and adding more complexity with cubic models does not significantly improve the fit. This shows that the quadratic model is the most suitable and efficient choice for representing on the relationship in this data.